The human kidneys face a continuous physiological paradox. They receive 20% of the entire cardiac output, a massive volume of high-pressure blood, yet must filter this violent flow through fragile, ultra-thin glomerular capillaries. If the kidneys were directly exposed to the unfiltered force of the circulatory system, the results would be disastrous. A light jog would cause immediate barotrauma and burst the capillaries, while the natural drop in blood pressure during deep sleep would bring filtration to a complete halt. This text highlights the exact biophysical threat the kidneys are up against. Systemic arterial blood pressure is the strict product of cardiac output multiplied by total peripheral resistance. Expanding that further, cardiac output is dictated by stroke volume and heart rate. Every time your heart beats faster or pumps harder, systemic pressure spikes. The glomerular capillaries lie directly downstream from this volatility. Today, we are going to dissect exactly how the kidneys manage this threat. We will master the mechanics of intrinsic autoregulation, trace the systemic renin-angiotensin cascade, and analyze the clinical pathophysiology of ionic balance. To survive the constant fluctuations of the heart, the kidney must possess localized internal vascular mechanisms that can completely sever its delicate microenvironment from the equations governing the rest of the body. The first line of defense is the myogenic response. This is an instantaneous intrinsic mechanical reflex hardwired directly into the vascular smooth muscle. The entire process begins with a physical force. When systemic blood pressure surges, it drives an excess volume of blood into the afferent arteriole, which physically stretches the vessel wall. This mechanical stretch forces open stretch-activated, voltage-gated calcium channels, located right on the sarcolemma of the smooth muscle cells. Extracellular calcium ions immediately flood into the intracellular space. This sudden influx of calcium is the direct chemical trigger for smooth muscle contraction. The arteriole clamps down. This localized vasoconstriction drastically increases local vascular resistance, artificially dropping the hydrostatic pressure of the blood before it can reach the downstream glomerulus. Through this localized reflex, the kidney generates an immediate physical shield, ensuring capillary hydrostatic pressure stays constant, regardless of the hypertensive storm occurring in the systemic circulation. The kidney also deploys a second, highly sophisticated regulatory pathway, tubuloglomerular feedback. Instead of relying on a simple mechanical stretch, this system uses a specialized sensory effector loop to measure actual filtration performance. This sequence details how the loop corrects a failure. It starts when high systemic pressure manages to drive up the glomerular filtration rate, pushing tubular fluid through the loop of Henle far too rapidly. Because the fluid is moving so fast, the ascending limb is robbed of the physical time it needs to properly reabsorb essential solutes. As a result, abnormally high concentrations of sodium and chloride ions arrive downstream at the macula densa, a patch of tall columnar epithelial cells lining the early distal tubule. These cells act as chemical sensors. When they detect the excess sodium and chloride, they actively import the ions using NaK2Cl cotransporters. Once inside, the cells respond by hydrolyzing intracellular ATP, breaking it down and releasing the signaling molecule adenosine across their basolateral membrane. That adenosine doesn't travel far. It binds directly to A1 receptors situated exclusively on the smooth muscle cells of the adjacent afferent arteriole. Binding to the A1 receptor triggers an intracellular calcium rise, forcing the afferent arteriole to constrict and choke off the excessive blood flow, returning the filtration rate to normal. This tubuloglomerular feedback guarantees that the filtration rate is continuously tethered to the nephron's ability to reabsorb, preventing the rapid, fatal loss of total body water and critical solutes. Local autoregulation works brilliantly for day-to-day fluctuations, but during a severe hemorrhage or a state of chronic sodium depletion, the kidney abandons local maintenance. It must initiate a systemic rescue. That systemic response is coordinated by the Juxtaglomerular Apparatus.
This multicellular junction consists of the sensory macula densa cells, supportive extraglomerular mesangial cells, and the endocrine juxtaglomerular cells. The juxtaglomerular, or granular cells, are specialized modified smooth muscle cells built right into the medial layer of the afferent arteriole. These cells synthesize and store renin. They will release it into the bloodstream under three specific conditions: a sharp drop in afferent perfusion pressure, a decrease in sodium chloride delivery to the macula densa, or direct sympathetic stimulation via beta-1 adrenergic receptors. By linking mechanical pressure sensors, chemical solute detectors, and direct neurological wiring, the Juxtaglomerular Apparatus serves as an elite endocrine command center, capable of hijacking the entire cardiovascular system to keep the body alive. This enzymatic cascade outlines what happens next. Once released, renin acts as a highly specific protease in the bloodstream, locating and cleaving a liver-synthesized plasma protein called angiotensinogen. This initial cleavage yields angiotensin 1, an inactive decapeptide that must now travel through the systemic venous circulation all the way to the pulmonary capillary beds. The dense capillary network of the lungs is lined with angiotensin converting enzyme, or ACE. In a single pass, ACE cleaves angiotensin 1 down into the highly potent vasoactive octopeptide, angiotensin 2. Angiotensin 2 executes 4 primary directives to restore blood pressure. It drives heavy systemic vasoconstriction. It constricts the efferent arteriole to preserve filtration. It prompts the adrenal cortex to secrete aldosterone, and it acts on the hypothalamus to trigger thirst and ADH release. Because of its extreme hypertensive power, shutting down this pathway is a major focus in clinical pharmacology. This text covers angiotensin receptor blockers, or ARBs, such as losartan and valsartan. Rather than inhibiting the ACE enzyme in the lungs, ARBs work by directly competing for the AT1 receptors on vascular smooth muscle. By blocking angiotensin 2 from binding, they force systemic vasodilation and lower blood pressure without inducing a dry cough. The RAAS pathway is the human body's ultimate volume rescue protocol, making its precise enzymatic steps the premier target for modern cardiovascular drug design. All of these macroscopic adjustments to blood flow and volume exist for one microscopic purpose: maintaining strict ionic balance and osmolarity in the extracellular fluid. This reference sheet highlights the narrow survival parameters. Total plasma calcium must stay between 8.5 and 10.5 milligrams per deciliter, while potassium is held strictly between 3.5 and 5.2 milliequivalents per liter to ensure normal muscle contraction and nerve conduction. Sodium, the primary determinant of plasma osmolarity, requires equally strict regulation. When plasma sodium concentration exceeds 145 milliequivalents per liter, the patient enters a state of hypernatremia. Clinically, hypernatremia rarely means a patient consumed too much salt. It almost always indicates a severe deficit of free water, a state of profound dehydration or excessive renal water loss. When free water drops, the concentration of sodium spikes. The extracellular fluid becomes aggressively hypertonic relative to the inside of the body's cells, establishing a massive, destructive osmotic gradient. Water is forcefully pulled out of the intracellular space to balance the gradient. When this happens to cerebral neurons, the cells physically shrink and deform. This physical cellular deformation is why a systemic fluid volume deficit initially presents as a severe neurological crisis, manifesting as confusion, extreme neuromuscular excitability, seizures, and eventually coma. The interconnected logic of renal physiology is clear. Local mechanical stretches determine whether brain neurons maintain their size. Locally, calcium drives the myogenic response, and adenosine powers tubuloglomerular feedback. Systemically, renin is synthesized by juxtaglomerular cells, while ACE acts in the pulmonary endothelium. These review questions outline the core biophysical concepts required to master the material. Pause the video here and test your active recall. Memorizing the names of the final Cascade products isn't enough. True clinical intelligence requires understanding the step-by-step biophysics driving the system. See you next session.